Well, thank you very much, Emmanuel, and thanks to the organizers for organizing this really nice conference. It's really a pleasure to be in Corsica all the time, and it's really a pleasure to be in a group like that. So that's great. And so I would like to talk about some joint work with Jan Guo and Klaus Wiedmeyer that is going to be about the asymptotic stability of some special equilibriums for 3D Euler equation. Okay. And so this is the final result. So the goal is to construct global solutions for 3D incompressible Euler equation in 3 dimensions, so there will be no boundary. And the point is that they will really evolve in a non-trivial way. And so what we're going to do is look at, so this is the equation that we want to consider, the model. And we want to construct small axisymmetric perturbations that are global in time. Now, there are a few things that may be a bit suspicious here. The first one is that you get global solutions for 3D Euler. This is really difficult. Many people do expect that most of them develop singularities in finite time. And the other one is that, so here you could say, OK, but this is only for small data. But of course, for 3D Euler, because it's so geometric, this is not going to give you anything, because you can always rescale time and the velocity. And initially, you don't really see this, but you see that whatever size for your initial data, you have now a small initial data. So for Euler itself, you would not really expect that smallness gives you anything. It just changes the time scale, but that's it. However, here, we're not really rescaling everything. We're saying that our solution will be of the type one fixed equilibrium, which is a stationary solution to Euler, plus a small perturbation. And so there you can't really play that game. So then it is conceivable that, or you're really talking about stability of this one. And if this is small enough, then you will have a global solution. The other keyword here is axisymmetric. However, our solutions will be axisymmetric, but with swirl. So they are not really inside the context of the global existence for axisymmetric without swirls for solutions. And finally, the other thing I wanted to mention is the relation with everything that we have seen so far is that up until now, vorticity was really concentrated in a tiny region. Here it is somehow the opposite. So vorticity will be everywhere. And somehow this is really the main driving point, because you can look at the curl of your vector field, and this is a curl that is uniform. And so it's 2 times the vertical vector. And this is small, so it's going to become 2 plus or minus epsilon. But so the point is that now you have vorticity everywhere. And what we're going to see is that we can find a condition on the perturbation, so a norm, such that if this norm is small enough, then our initial data is going to lead to a global solution. And moreover, this small perturbation is going to just go back to the equilibrium. It's going to go back by linear scattering, and it's going to decay uniformly at a rate that we will see is the best you can hope for. But on the other hand, as at several points Louis pointed out, is that this rate 1 over t is really not enough to directly handle the nonlinearity, so you need to be careful. And you need to do some work to treat it. OK, so let me try to give a little bit more context about this. So this is the bigger question of this is that you can construct a lot of trivial solutions to 3D Euler by just taking a solutions to 2D Euler and then extending it in 1 dimension with trivially. And moreover, you can find a lot of equilibria for 2D Euler by just taking a case when the vorticity is radial. This is going to be a stationary solution. And this is what we do. And moreover, we will do it for the simplest case. And so that's the vector field that would be associated with just rigid motion. And so you can verify if you take this vector field, this pressure law, then you will have a steady solution to 2D Euler. And now if you want to understand perturbations of this, then you want to look at, you write your equation as this plus this small perturbation. And what happens is that you obtain this model, which I will call the Euler-Coriolis model. And now the advantage is that this is just for this little u, which is a small solution, and which is the thing that we will focus on from now on. So the Euler equation is one way of thinking about what we're going to do, but really for the rest of this talk, this is the equation that we will try to understand. And the name of the game is to say that if I would like to make sure that 0 is stable for this. So if I start with a small enough data, then I will have a global solution. And if it's axisymmetric, then I'll have a global solution. And I can even understand what is going to happen later on. And so in this case, it's related, in this sense, it's related to some other work in the last decade that started a lot of interest, which is the case of this other specific equilibrium for 2D Euler itself, the Couette flow. And then you look at a small perturbation. And Bedrosian and Masmoudi, for example, showed that if you start with a smooth enough and small perturbation of this, then you will still, so this guy is going to exist globally and will slowly converge to another shear flow. However, in our case, it's going to really the key word will be dispersion, and the dispersive mechanism is going to be what drives all of the dynamic and what we need to expect. So the at some point the analogy breaks down, but at least it's part of the same idea. So somehow this never really accept. Okay. Now, there is another way of thinking about the Euler-Coriolis equation. If you don't want to start with a solution to the incompressible Euler equation and look at the perturbation, you can also think of it in this way. You start with your aquarium. So this would be whatever is inside is modeled by the Euler equation, and now you just start spinning it. And you look at what happens in a frame that rotates with your aquarium. And if you do it, and so in our case, it would be a very big aquarium with no boundary. But what you should see should satisfy the Euler-Coriolis equation. And now, of course, you can say, OK, why would I care about that? Why would I decide to move my aquarium? Well, in some sense, there are some cases where you do live in a rotating frame. And so you do want to understand what this additional effect of rotation is going to, well, what dynamical implication it's going to have. And so, OK, so this is the Earth. So obviously, this is our setup is really a modelisation or a simplification because our Coriolis parameter is going to be constant. We also live in a, we have no boundary and we live in a flat space. But somehow, at least the way I think of it is that it would be at medium scale. And you can still think that the Earth is flat. You can still think that the Coriolis parameter is constant. And then this is what you should see. OK, and again, so in general, in this case, you will have a lot more physics that you need to understand. And so people here have looked at it. This is not, so this is too complicated for us. We want to stay with a model as simple as possible and just really focus on the effect with rotation on the one hand and the incompressible constraint on the other. And so this is where we will really focus on. However, the advantage of focusing on a model, on honing in on this model, is that we can go beyond some of the limitations that you can have in other cases where you would focus more just on the linear analysis. And we will see that in our case, there is a lot. So you need to understand the linear analysis of your problem, but then there is really a lot more to do. And also, so you add more forces, more physics, but then you send some of your parameters to 0, so you also remove some of them. So in our case, there is just one parameter. It's the size of the initial data, and it doesn't go to 0. It's just that if it's small enough, things are good. So you win some, you lose some, but this is, at least we have a simple problem. Now, this Euler-Coriolis problem is really related to two works in mathematics that had a lot of influence. And so at least it's better to present them and then try to contrast them a bit with what we do. So the first one is by Bobin, Mahaloff, and Nikolenko. There was also work of Emmanuel Grenier, at least. And it's looks at solutions to the Euler-Coriolis equation, now on a compact domain but with no boundary, on a generic torus. And what they say is that you can decompose your solution that satisfies this complicated 3D dynamic into 3 pieces, each piece being a lot simpler than the beginning. So the first piece solves just a 2D system. So at least you've reduced one dimension. This is something you can handle. For example, you do have global solutions for 2D Euler under fairly mild conditions. So this is something that you would think of as a lot nicer. The second piece solves a linear equation. So in this case, there is really no question that the solutions are global. There is no question that you can really understand them as much as you want. So that's nice. But on the other hand, it does live in 3 dimensions. And then the third piece, well, you don't really know anything about it. But at least you know that if you spin your aquarium fast enough, then it is going to be small. At least for, so you fix your interval of time and then you spin fast enough, this guy is small. So, well, at least this is good enough. If you decide what error you can tolerate, you spin fast enough, and then you really only have to understand those two dynamics, and that's something that you can do. So that's the first result about the Euler-Coriolis. Then another result about the Euler-Coriolis, so this time really in the same domain as the one that we want to consider in R3, was a work of Coley and Takada, but there were earlier work by Duty-Froid, and then later work by others. So again, in this case, the point that you want to do is I fix my initial data, and I fix how long I want to look at it. Then if, again, I spin my frame fast enough, I can guarantee that this solution is going to live at least up to this time. And so they do more of this. I can allow some fairly low regularity solutions. And another thing that is good to remark now is that in both cases, there is no need for axisymmetry. And so we'll try to understand where this axisymmetry comes in later. But something that you can see, at least if you are in the business of understanding the effect of dispersion on equations, is that here you see the two hallmarks of dispersive equations. The first one is that you have oscillations in time, and you can do normal forms to say that the effect of the nonlinearity is going to happen a lot later than you would expect, except for some resonance system that you just can't remove, but that hopefully is going to be a lot simpler. And the second part is the effect of dispersion. That says that, well, if you have a lot of volume and you start with a compact set of energies, then the waves are going to have a tendency to disperse, and so they should get smaller over time. So maybe in a picture, so if you have a general dispersive equation, say just you think of what happens, just linear dispersive equation, so you can construct your solution as a superposition of wave packets whose behavior is going to be fully determined by the dispersion relation. And more precisely, their dynamic is just going to consist of two things. So they will translate uniformly in time at a speed that is given by the wave velocity, so something that you can compute from the dispersion relation. And at the same time, they will also have a phase that oscillates in time at another velocity, the phase velocity, that is itself exactly the dispersion relation. And so you see that if this is if your solution is really a sum of wave packets, so the linear terms, then there is nothing to understand because you can just understand them one at a time and then add that. And then for the nonlinear terms, the nonlinear interactions, well, at least they will be really strongly curtailed because for two different, well, one wave packet can interact with itself, so that you have to deal with it. But two different wave packets that would correspond to two different kind of information, for them to interact, they need to be at the same location in space-time. And if they move at different velocity, this is only going to happen for so long. And not just that, when they are at the same place, then you're going to, for their interaction to really be constructive, then you would need their phases to be the same, because otherwise you're basically integrating a cosine, and this is not going to evolve over time. So you have these two facts, and so normal form has to do with the fact that if you have two wave packets, no matter where they are, but if they oscillate at different time velocities, then they will never have constructive interactions. And the dispersion is here, or the Strickard's estimate capture the fact that if you can decompose your solution into a lot of different wave packets, and in general, their interaction is going to happen on a much smaller space-time region than you would have expected naively. And so the two previous works, one was trying to use this fact about the time oscillation, the other one was trying to use this fact about the dispersion. And what we would like to do is to combine the two facts to see if we cannot go further to treat the whole space R3, and then try to really go not just for a logarithmic gain, but t equal infinity, and not have to spin the aquarium too fast. Now, one last thing about this. So the question about why would you gain, or how does it? So in our case, we fix the speed of rotation to be 1. In the other works, you would let your aquarium rotate faster and faster. What is the relationship? Well, of course, you can always rescale time. So if you think that you rotate at fast time, you can always just rescale time to force to see only one spin per minute. And then you would change your Euler-Coriolis to this equation. And your initial data, instead of epsilon, has become this guy, so epsilon times u. So you started with an initial data that was of size 1, but now just by rescaling, you're really considering a small initial data. In fact, a vanishing initial data. Your nonlinearity has become a little smaller. And on top of that, you're looking at a very fast dynamic, a very fast dispersive dynamic. And now if you think that what dispersion tells you is that whatever is located close to the origin is going to move away, and everybody is going to move away from each other at a certain time. And now you speed this movie. Now everybody moves very far away from each other very fast, and so their interactions will be all the smaller, ever smaller. And the way to capture that is that you can do, for example, what Louis presented. So a good way to capture the dispersion is through those Strickard's estimates. And if you can do it when the speed of, if you can have good estimate, so you need some quantitative term. You can just get one quantitative term when the speed of rotation is 1, and then just see what rescaling does. And it tells you that any information that is stronger than just the energy is conserved. So if here I don't have infinity, but I have a p that is less than that, so something that would really be sensitive to the time of the region of interaction, then just by simple change, it's going to pick up an epsilon. And when I start measuring my norms, I can get epsilon in all of those nonlinear terms, and it makes it a lot more likely that I can run a fixed point argument. The case of the normal form is the same. It's just a little harder to see exactly where in the analysis it helps you. But one way to think of it is that doing a normal form is integrating your equation at least to first order. So you can think of it as just dividing by dt, d by dt. And if now you divide by the fast time, then once you do that, you gain an epsilon. And this is why, well, wherever you could divide by dt, then is the same, but epsilon times that. And so you can at least neglect it for some time. All right, so, well, we won't try to gain here, but gain from the, but what we, so we will set, in our case, epsilon to be 1. And we'll try to really not just gain from the existence of this small parameter. But now there is one limitation, which is the fact that we really need this axisymmetric data. And maybe it's not so clear where it comes from. even though in fact it was there in the previous work, it's that there was this resonance system that somehow is outside of the scope of the analysis. So it stays there even when you do a normal form. And this is the case that this is the thing that we can't really tolerate, and this is where we use the axisymmetric assumption. I'll try to explain it a bit more later. But so from now, this is it for the general context. Let's focus on this equation that we really want to understand, Euler-Coriolis. So in other words, at least the way I think of it is that I want to understand the influence of this term, the rotation term, on just something that would tell you that you just have convection and conservation of volume. What is new? What happens? And so if you want to understand an equation, you first want to see, OK, what are the symmetries of this equation so that I'm not just studying the same thing but in a different chart or via a simple transformation. So the first one are just the symmetries of the equation. So you start with Euler, which is fully geometric, which as a result has a ton of symmetries. But now that we've added something else, then it's less symmetric. So for example, in Euler, you can rescale independently space, time, and velocity. And now you need one relation to combine them, but that leaves you 2 degrees of freedom to rescale your equation and still get the same equation. Now we force the speed of rotation to be 1. In some sense, this was what we discussed before. So now we really just have one scaling symmetry for our equation, but you can still decide on the arc length or the length in one way, and then you can just change the way you measure velocity, and you would see the same equation. Same thing, Euler was completely isotropic, but now we really force the axis of rotation to be the z-axis. So we only have symmetry by if we change our frame to any other frame along this axis. So this just gives us 2 places where two symmetries for our equation, and then related to this, it gives us 2 natural derivatives where we can basically for free derive our equation 2 different directions. The first one coming from the infinitesimal generator of the scaling, so it is basically x dx, and then the second one being the infinitesimal generator of rotation about the z-axis. And what you can observe, so somehow this was something that was really realized in the 80s, that sometimes just understanding the scaling of your equation basically gives you all the things that you want to understand the dynamic because, well, you're already so constrained by the symmetries. So this is, for example, a good way to understand the wave equation. And another way to think about it is that, so we would like to say that somehow we would like to understand the behavior of this guy, U. And so what does that mean to move little? That means to stay in a compact space, but you're, of course, moving in an infinite dimensional space. So, so how do you get compactness in a set of functions? Well, you want to say that you don't really change when you have uniform continuity of translation, so you don't really change too much when you move, when you translate, and that the support remains where you expect it to be. So this is about staying uniform continuity of translation, or in other words, staying at high regularity. And it tells you that there are 2 directions in which if you derive, you will basically for free stay very regular in those directions, but we live in 3 dimensions. So this is not enough by itself. And so it's part of this series of problems where you would like to use those vector fields that are handed to you for free, but they're just not enough to do all the work, and so now you need to develop some toolbox to use this, but it's not enough. Okay, and so this is more for later, but what we're going to do, and maybe also a question for if you can help me understand it. So we know that our solutions, we can derive them in 2 natural directions. The scaling direction and then the rotation about the z-axis direction. Now, those happen to be the first 2 vectors of the spherical coordinate basis. And so we're going to, so we need to understand derivatives in all directions. So we're also going to add derivative in a third direction, which is the third vector in the spherical coordinate basis. So all of those vectors, they commute with each other. So if we have information about derivative in this direction, we know for free that it's not already accounted for by derivative in those directions. So that's good. On the other hand, this has no particular nice properties. So there is no trick that we can use. This is just brute force to try to propagate regularity in this direction. But here is something at least I am a little perplexed by it. So in my problem, the only natural basis that I would have imagined would be the axisymmetric basis that could play a role. And somehow here it's really the spherical coordinate basis that is handed out to me by the symmetries, and I don't quite see why it is that, but on the other hand, that's what it is. Okay, and this is, so the first thing about the Euler-Coriolis equation was to try to understand its symmetry. The second and the most important fact about the Euler-Coriolis, or at least for us, about the Euler-Coriolis equation, is that it is a dispersive equation. What does that mean? That means that if I start with small initial perturbation, then I can just forget about the nonlinearity, and what remains is just this equation, which is sometimes called the Poincaré operator, as far as I understand. And this, well, it really looks like Euler equation, but somehow it is a lot better. And what is, at least was, is not directly apparent, but you can do after some work, is that this is in fact a dispersive equation, meaning that if you choose the right unknown, then you can basically change it to this, which is almost the equation that Louis talked about. So he talked about the Schrödinger equation, which would be the case if the dispersion relation lambda was the Laplacian. Now, in our case, the dispersion relation is something that you can compute, and it is this kind of bizarre function, xi3 over absolute value of xi, which, okay, this is degenerate, but at the very least, you can see that it is something that does depend on xi. So there will be this fact that two different wave packets, or most two generic wave packets, will move in different directions. Something also that I find quite interesting, and I don't, again, have a good understanding of it, is that this dispersion, not this dispersion relation, but something very similar to it, also appears in a different setup, which is the case if you consider a stratified fluid. Interestingly, so for us, the dispersion relation is, and of course it is, it's the cosine of this angle. In the case of stratified fluid, the dispersion relation is, so it's not the same as us, it is the sine. And those two have different properties, but still they are very much related. So, yeah, I don't know why is there a connection and what does that tell you, but I thought it was quite striking. Now, because we're talking about a dispersive equation, we really need to take some time to understand the dispersion relation. The dispersion relation is, so it's an explicit function, so at least we will understand everything about it in finite time. In this case, you can see that because it is zero homogeneous, Euler equation tells you this kind of bizarre fact that the group velocity, the gradient of the dispersion relation, is going to be perpendicular to the frequency of oscillation all the time. So this is strange. So if you have a wave that propagates or that physically oscillates in this direction, it's going to move in that direction. But okay, that happens. Again, you can compute everything explicitly. If you're a dispersion relation, so if you want to have a bona fide dispersive equation, you would like the group velocity to really depend on your frequency. So you, in other words, you want the Hessian of the phase to be non-degenerate. The Hessian is a bit complicated, but at least in cylindrical coordinate, it's a nice matrix. And in particular, you can compute its determinant, so you really know. So you see a lot of good news there, in the sense that, well, sometimes it's going to be degenerate, so that Hessian does vanish, but you know exactly where. And you know that in the frequency space, you will be good away from two different regions of oscillation. If you only oscillate in the vertical direction, so for functions that only depend on z, or for functions that only depend on x and y, and we'll see that those play a role, there is no dispersion. There is no oscillation. The Hessian vanishes. But at least if you take a frequency region away from those, then you are fully non-degenerate, meaning that in this case, the decay should be the generic decay in dimension 3, which would be t to the minus 3 over 2. That is a really good news, because then if it was the case, my nonlinearity, at least assuming that I don't really lose too much information, that I can just take the absolute value there, then they would be of size t to the minus 3 half. That should be integrable over time, so I would really expect that nothing very much happens. So if I take a box away from one of those places of degeneracy, then I get very nice decay. I know things are bad here, but those are really not of full dimension. So the question is, how do things degenerate when I approach some of those regions? And so I know that things are going to be the right thing, but they generate depending on the distance to those bad regions. And in this case, they generate so you can compute it with a bit more work. And so they degenerate. Let me just see. So if this was the height, and let's say this is the distance this, and if the height is the smallest, it would be h to the minus 1. And then something else that I can do, if I want to understand the contribution of this frequency, is to just forget that I have any oscillation and just integrate trivially, in which case I would get the volume of this pole. And let me assume that I have rescaled such that at least one of those two is 1. So this is really the decay that I can have. And so if I look at the envelope of the decay for all of those contributions, then the best I can do would be 1 over t. But I know that this decay comes from trying the worst case scenario in a lot of elementary bricks, each of which was much better than that. But if for any position and any time I look at the worst case, it will be this. So yeah, that's it. You can hope that maybe we've not done the analysis well enough, and so you can improve on it. But in this case, it turns out that there is nothing you can do. 1 over t is the best decay. And in some cases, you can really see that this is it. OK? Maybe this is more a remark to say that this is, so there is a direction of work in the analysis of dispersive equation, which is to try to understand ever more complicated dispersion or dispersive equation, starting with the simplest case of the wave equation, the Schrödinger equation, where things have a lot of spatial, well, you can understand things better and you have more properties, and then trying to go with more general and natural dispersion relation, like the one that you would get from gravity capillary water waves, which is algebraic but still more complicated. But somehow, up until now, it has mostly focused on the case of a radial dispersion equation, which is quite natural. And my guess is if you think of most of the equations, the simplest equation, that would be the case. And somehow it turns out that this has a lot of hidden constraints that come with having a radial function. And so this is one step in trying to go beyond that, understanding a non-radial dispersion relation in one case. Well, in our case, it is axially symmetric, so it is not radial. It is the first step away from this. OK? And before we get into, I say more about how we go about analyzing it, I need to finally try to explain where this restriction of the axis symmetry comes from. And this comes from some special family of enemies that are not really there, but almost there. So what do I mean? So the whole predication of our analysis is that because we can think of it as some, even though it comes from Euler, it is some variant of the Schrödinger equation that Louis presented, things will be well. Now, this only works if we can make sure that everything behaves as a dispersive equation. Otherwise, we'll have to. This was a wrong starting point. And it turns out that you can find a few solutions which are definitely non-dispersive, but they're all degenerate. So the first one is a kind of trivial case. So you would consider a vector field that only depends on the vertical variable and always points in the planar case. And then you let that rotate at uniform speed. Now, this would be an exact solution to the Euler-Coriolis equation, and this definitely does not disperse. It basically doesn't evolve. So on the other hand, you would say this is really far from small data. This is really far from something that can be approximated even by a compactly supported initial data, because it's independent of, it's invariant by translation in two directions. So that's not exactly within the scope of the data I can consider. That is true. On the other hand, since this is a good exact solution, I can try to localize it to produce a lot of approximate solutions. And now in my analysis, it would be very hard for me to distinguish between an exact solution and an almost solution if it's good enough. And I can localize it and then compute it, and then I can see that this is a pretty good almost solution that would now be compactly supported, in fact. So where do I gain? Well, in this case, so I haven't told you yet what the norms are that we're going to consider, but basically our norms are going to strongly dissuade you to behave only from in the z direction. Or in other words, in our norm, those solutions will just not be small, and so then they're really not within the scope of solutions that we want to consider. So those are not so relevant. So those end up not being so relevant a posteriori. Now there is another family of exact solutions that are not dispersive at all. They come from there are solutions that now depend on the two other variables, only of the planar variable. And the first two components of the vector field, they satisfy the 2D Euler equation. The third one is just passively advected by them. So why would they satisfy the 2D Euler equation? Well, if you just write the Euler-Coriolis in this case, you will get this. And then the Coriolis forces, you take your vector and then you rotate it by 90 degrees. But if we're in 2 dimensions, and I have a divergence-free vector field, this is a grad perp. And if I rotate it once more, this is a gradient. I can just incorporate it into the pressure. So this is really to the Euler equation. And now to the Euler equation, I can solve it. I understand what happens, at least to some extent. And at least I know that this is not dispersive. So it's a bad news. Once again, it is not going to fit into the kind of initial data I have. But on the other hand, if I start localizing them, then I can really produce pretty good approximate solutions to my equation. And those are the ones that I just don't know how to handle. And so this is why we impose the axisymmetry for our initial data, because that would because then the consequence would be that those should be radially symmetric solutions to the Euler. And so they don't evolve. They are 0. And so then, in fact, they don't exist because of the axisymmetry assumption. And so those almost solutions are not relevant. But, well, this is really the main limitation in our work. If we wanted to go to treat a general perturbation, we would need to see something that looks like this, at least for a long time, and then disperses. And that's really tough. Okay. Yeah. Yes. So, well, no, but yes, absolutely. So, I mean, at least the answer to your question is no, we can't really do this. This would be very naturally fitting into our equation, but more, at least the way I would think of it is more, the case when the vorticity is not just, so in my case, I look at perturbation of 2D solution whose vorticity would be radial but would be R, would be 1. And this gives me rigid body motion, and then I look at perturbations of that. The really interesting problem in this case would be to look at those exact solution, steady solution to 3d-Euler, and look at perturbation of those. And that would be really interesting. In some sense, this is trying to understand the foundation for it, but it would really be a different problem and depend on the thing. But so lots of relation, but at least we can't really say anything. And in our case, even less so, because in this case, we want to ensure that this guy, at least the perturbation of this one is trivial. So we force it to be 0. But it was, but the 2D solution was somehow in the equilibrium that we removed from the beginning. All right, I don't know. I hope that's clear enough, but I'm happy to say more. In some sense, this is really the most difficult thing to understand, because those solutions, those non-dispersive solutions, are not within my class of solutions, but they give me almost solutions that are too close and that I would have to be able to handle. And so then I don't really have a good tools to understand them. Now, okay, let me maybe say quickly a few things about the proof, which is so fairly technical. And then the nonlinear analysis is, I'm going to slip it under the rug, but if you have any question, I'm happy to discuss it. But at least, what are the big outline of it? So, and those are basically specific problem independent. The first step that you always want to do is to find a good parametrization of your problem to basically get rid of the geometry and reduce it to a dispersive equation for a scalar problem. In our case, we can do it. The second one is to really understand the linear solution, the linear operator inside out, and really see, well, making sure that for most of the blocks, we can really obtain something that would make them less relevant than if we were to look at the worst case scenario and really see that what is the worst case scenario that we have to handle. So really understand the linear problem very good. And the analytical part of it was that it's going to decide what is one of the components of our norm, the way we measure the size of the data, because one of the things that is going to make or break our work is to find a weak enough criterion that would still ensure that we have the optimal decay. Because if we had decay smaller than 1/t, then things would be a lot harder. And then after that, well, then there is something that is by now basically for free, which is that if you have good symmetries of your equation, then you can always derive along those directions. So this is easy in our case. And then after that, it's really starting to think of our equation as a nonlinear dispersive equation and try to turn the crank of this toolbox, the corresponding toolbox. So in this case, we do it in two ways. The first one is to improve the estimate that we get for free on those derivatives, which is control of some energy, so some L2 norm, and to push it to a norm that is better suited for the dispersive analysis, which would be f hat in L infinity, or the saying that, yeah, which would be a norm like this. So this is a stronger norm. We want to construct an L2 norm that would have the same properties, and then try to work to control that. And then the last part is really where the brute force comes in. It's the fact that all of this was really striving to control our solution when we derived it in the good direction. But this is not enough. We also need to derive it in the bad direction to have full understanding of its smoothness property. And so, and then because it doesn't work well, we need to handle fractional derivative along for a derivative vector field that is not flat. And well, then you need to develop the tools for it. All right, and now quickly a few words about the first few steps. So the first one is about the parametrization. So I guess Monica presented it that if you're axisymmetric, then you have a natural representation of your vector field, the swirl stream formulation. So it will be here. And so that is quite nice because it allows you to have two scalar unknown instead of, say, the three that you would have for a vector field. And they also are a good way to understand, say, how the energy is distributed. So this would be a natural way to try. However, for us, we will really rely on the dispersive properties. And for that, we want to use at some point the Fourier transform. And then that's a lot harder to see how those guys behave. So instead, we're going to use a different formulation, which is the Hodge decomposition of the horizontal component of our velocity. And then the third one is and then the third component. Why did we get there? Well, this has to do with, we computed the linear problem, which was dt of u is equal to the rotation of u plus the gradient of a pressure that you recover from the incompressibility relation. This is a complicated 3x3 system, and but you would like to diagonalize it. And well, you play with it a little bit, and then you can see that if you consider so the third component, and then the other one, the planar component, was we saw that it has some connection with 3d-Euler, so you can think of the curl of the planar component. Then you see that at least instead of a 3x3 system, you have a 2x2 system of those. The nonlinearity that used to be very simple in the previous coordinate is now complicated, but somehow for us we forget about the nonlinearity. So what is important is that we have this 2x2 system, and then this 2x2 system we can easily diagonalize it. And if you so you want to diagonalize it and also keep the right homogeneity. So at the end of the day, these are your two unknowns, but it's basically taking the vorticity, the horizontal vorticity, and an antiderivative of it. And then this is more renormalizing the third component. So once you look at it, then you can be afraid that, OK, this may be diagonalized my linear system, but how well is it related to how do I recover my velocity field from those? And it turns out that, in fact, it's not so bad. Or it's, in fact, it's OK. So the vector field is given in a relatively smooth way, even though it involves a lot of Fourier multipliers in terms of your unknown. And not just that, the energy has the same decomposition of the energy as before. And even the good derivatives, they have the same good decomposition as before. And if I can take 1 more minute, I just want to finish, or to try to see how analytically do I see the relevance of the axisymmetric assumption. And this is at the next step. So now I have decided of my unknown to understand the linear part of the equation. It's here. If I wanted, I could diagonalize it. I mean, I can just look at a plus c and a minus c, and now this will be diagonal. But then I need to go to the next step, which is what about the nonlinearity? And the nonlinearity is now complicated because we saw that even in terms of u, it was reasonably complicated, and now u, I need to express it in terms of a and c, and so it becomes a mess. I haven't really tried to re-express it. Except that once you look at it, you can see that there are three kind of terms in the nonlinearity. The red, the blue, and the green. So the green are just the guys that I won't discuss. They are better than everything else. So these guys, and in fact, for us, they even vanish because they contain a derivative in the angular direction. So, but even if they did not, those are just very good. There are the blue terms. The blue terms, well, they're not as good, but at least they have some kind of null, some additional null component, which is that they are complicated multiplier, but they always involve the angle, something related to, or a function that would either vanish on that set or on that space in the Fourier space. And so at least where my dispersion is weaker, my nonlinearity is also weaker. So hopefully they get good together. Now, somehow all the cases happen here, so it only gives you a tiny bit of help, but still it gives you some help. And then there are the red terms, and the red terms, there is nothing I can do with them. They don't have any good property that I can see. And in fact, if you squint hard enough, you can see that at least, let's say, if I think of solutions that are independent of z, so where lambda, which is xc3 over xc, would vanish, then I basically have 2d Euler here. So if lambda is 0, this vanishes, and then what do I have here? I have that dta is equal to, let's see. So if I were to rename omega to be the horizontal gradient of A, I would get rid of this, and I would have that dt of omega is equal to the gradient of omega times the u, that would be the vector field that I would recover from this vorticity. So this is really a closed equation in A, and it is really 2d Euler. And then this, if lambda is 0, this vanishes, and this would be, again, that C is passively advected by A, by the vector field that I obtained before. So somehow you see that those non-dispersive solutions that were possible, at least they come from some nonlinearity that is trying to create them, and would create them no matter what I do. And those nonlinearity are just too bad to or at least I would not really know what to do. However, if I'm axisymmetric, then because those are radial derivatives, this would be in the radial direction, this would be in the radial direction, and I take their determinant, so both of those things vanish. And it is really the trace that my obstruction to having a dispersive equation is really, well, vanishes for axisymmetric data. And maybe I will stop here. So this tells you how to get the analysis started. Then after that, you need to turn a lot the crank to decide what are the good norms to get the dispersive equation, and then to see how you can make sure that you can control those norms by themselves to make sure that they remain uniformly bounded. But that's for another, or if you want, you can either look at the paper on arXiv, or you can, I'm happy to talk about it. But thank you for your attention.